Hello everyone, welcome to this video. In the previous video we saw that we can prove this result using the principle of mathematical induction. Now let's see another way by which we can prove this result. So let's have a quick look at the proof. So what we can do in the very starting, we can consider these two terms, k plus 1 raised to power 4 minus k cube. Now you would ask me why in particular we are taking these terms. So this is not clear in the very beginning, but when we proceed towards the proof, you will see that while solving for this expression, we would encounter with the expression like this: 1 cube plus 2 cube plus 3 cube and so on, right, up to n cube. So we will be indulged in calculating the value of this particular expression from using this identity. So let's first of all solve this identity: k plus 1 whole raised to power 4 minus k raised to power 4. What is k plus 1 whole raised to power 4? It is k plus 1 whole square multiplied with k plus 1 whole square minus k raised to power 4. So you can expand this term and this term, so you have these terms. Then further you can multiply these terms, so we would have these terms over here, right? Then what you can do, you can further simplify the terms, take the like powers together. You see this k raised to power 4 gets cancelled here. So we have this term and this term corresponding to k cube, which is 4k cube, right? And we have this term and this term corresponding to k raised to power 2, which is 6k square. Then we have this 2k and 2k corresponding to k raised to power 1 and plus 1. Right? So basically we have this thing equal to this thing. So this would be our identity, and we will be using this result further on in this proof. So what we are doing here is we are substituting the values of k as 1, 2, 3, so and so on up to n. So we would have these equations. When you substitute the value 1, you would have 1 plus 1 raised to power 4, which is 2 raised to power 4 minus 1 raised to power 4, that is 4 into 1 cube plus 6 into 1 square plus 4 into 1 plus 1. Don't try to solve this right hand side, because we will be utilizing this kind of structure further on in the proof. You'll be seeing this in a moment. Similarly, for k is equal to 2, we have this equation. For k is equal to 3, we have this equation, and we keep on doing like this. And we have, for k is equal to n, we have this expression, right? What we can do, we can add up all these terms corresponding to k, so that the left hand side of all the equations would be added together, right? And the right hand sides would be added together, right? Separately. So let's do that. First of all, our left hand side would become 2 raised to power 4 minus 1 raised to power 4 plus 3 raised to power 4 minus 2 raised to power 4 plus 4 raised to power 4 minus 3 raised to power 4. We keep on doing like this until our last term, which is this one. Correct? This is our left hand side. What about the right hand side? You see in each of the term we have 4 into something cube. So we can write all the terms like this: 4 into 1 cube plus 4 into 2 cube plus 4 into 3 cube and so on. So you can take 4 outside, so it would be 1 cube plus 2 cube plus 3 cube and so on, right? So this is what I have done over here: 4 into 1 cube plus 2 cube plus 3 cube up to n cube, right? And similarly you have the structure like this, consisting of all the 6 terms: 6 into 1 square plus 6 into 2 square plus 6 into 3 square and so on. So you can again take 6 as common, so you would have 1 square plus 2 square plus 3 square and so on within the brackets. So this is what I have written over here: 6 into 1 square plus 2 square plus 3 square up to n square. And next we have the structure of these terms: 4 into 1, 4 into 2, 4 into 3 and so on. While adding them, so we can take 4 as common, so we will be left with 1 plus 2 plus 3 plus up to n. And in the last we have 1 plus 1 plus 1. How many times? In total n times. So that, because we have n equations in total, so that means this would turn out to be n, right? So this is what our equation becomes. Now you see we have here we can cancel these terms. Similarly, in the next expression we would cancel these terms and so on. So all the middle terms would be cancelled. What about this last term? In the last term you see we have this n cube cancelled with the previous term. So we are only left with n plus 1 raised to power 4 minus 1 raised to power 4 in the left hand side, right? The right I have just copied down this right hand side here, right? So okay, next here you see we have this expression. So in this expression we wanted to actually calculate its value, because we know its value, right? Remember the last two formulas which we have studied. So we will make use of this formula and this formula over here. So when we make use of the formula for calculating the sum of all the squares, you see the formula is n plus 1 2n plus 1 divided by 6, and for calculating the sum of first n natural numbers, it is n plus 1 divided by 2. So just substituting the values over here, we have this expression. So this 6 and this 6 gets cancelled, this 2 and 4 gets cancelled, right? So we are left with these terms. Now from these terms, what we wanted to do, we wanted to evaluate this term here. So for evaluating this term, we can shift this term to left hand side, these two terms as well to left hand side, and then we can divide it by 4. So it would be 1 by 4, this term minus this term minus these two terms. This is what I have written over here, right? Next, this is equal to this term which we wanted to evaluate, right? So when you solve and simplify this term, you can club these two terms. This would become minus 1, this is minus n, so you can combine this minus n plus 1, right? So you have this term, this term, this term, and this term. So in all the terms you have n plus 1 as common entity, correct? So you can take it as common. So in this you would be left with n plus 1 raised to power 3, right? Here in this term you would be left with minus 1, here you would be left with minus n into 2n plus 1, and here it would be minus 2n, correct? Okay, so you can further simplify the terms. From these two terms, you can write these two terms as minus of 2n plus 1, right? And then you have minus n 2n plus 1, right? And then you have n plus 1 whole cube, right? So from these two terms you can take 2n plus 1 as common, in fact minus 2n plus 1 as common. So here you would be left with plus n, and here you would be left with plus 1. So this is the term combined together. Now in the next expression you can see here very clearly that you have n plus 1 here and n plus 1 here. So again you can take it as common. So when you take it as common, this power would now become the power as 2, and you are left here with the power as 2, and here you are left with minus 2n plus 1, right? So you can now further simplify the terms. You can open up this square here, n square plus 1 plus 2n, and you can open up this bracket, so it would be minus 2n minus 1, right? So this 2n and 2n gets cancelled, this 1 and 1 gets cancelled, so you are left with n square. And basically this is the formula for calculating the sum of cubes of first and natural numbers, and this is what we wanted to prove here in this video. So I hope you understood these both the proofs for this result. Well, that is it for this video. Thank you for watching.